Nice. So there's you already talked about the content a little bit of the seminar, and it's going to be, as I said, an astrophysicist take on geospatial data science. Let me just skim very quickly through the summary of this talk. And it's I'm going to start with some background, so just so you know who I am and where I come from on my astrophysical background, how sort of I transitioned to data science, and what is data science, what I'm doing now, what is data science in general, and the topics I've been working on. And also the overlap between the two fields, so astrophysics and data science. Then I have a few words about satellite data. When you do Earth observations, there's two main kind of observations that you can make from a physical perspective, in the sense that you use two very different kind of detections and of detectors on the Earth's surface. So it's multispectral images and synthetic aperture radars. One is a active kind of detection, so with a radar, and the other one is a passive system. And then I'll talk about the applications. So that's sort of the interesting part of the talk, I hope. So what you can do with AI and machine learning to analyze these images, how you can build data sets, how you can train machine learning and artificial intelligence systems to perform operations on these images, and some applications in the field of geodata science, in the sense that we, with my company, we've been working on a few projects where we use this data in combination, of course, with other data sources to analyze natural trends like greening or reduction of greening and stuff like that, or natural risks, so natural hazards like fires and floods and things like that. So how we can use this data to develop systems for natural risk detections and prediction. So let me start from my astrophysical background. I think I skipped one. Okay, so this is the first project I've been working on. I've been doing my PhD in Madrid with Professor Alexander Knebe on n-body simulations of different dynamical dark energy models. So beyond lambda CDM, I hope you are all familiar with lambda CDM. I'm assuming that. So I've been studying those kind of beyond lambda CDM models, so with dynamical dark energy that is changing with time, and it's not just a cosmological constant. And these are just some of the papers I've been publishing, and the topics I've been working on for the first years of my astrophysics career. Then I switched to some more visible things, in particular the local universe. So everything that concerns the local group of galaxies, so the system of Andromeda and the Milky Way, and all the small galaxies that orbitate around these two main spiral galaxies that make the local group, as well as the local universe in the sense that of the nearby clusters such as Coma, Perseus Pisces, Virgo, of course, and so on and so forth. So we try to simulate these systems in a very realistic way, and we want to study. We try to study with Professor Yehuda Hoffman in particular. We studied the evolution of these clusters. So we wanted to sort of reconstruct the history of both local group galaxies as well as the local universe galaxy clusters. So on two different scales, but the techniques we used were pretty similar. And then in 2020, something happened, as you might all know, and I decided to take a turn in my career. So I started studying data science, but within the context of astrophysics. And so my first data science project in astrophysics was this paper that we published last year. And it's using a quite simple machine learning algorithm that's called gradient boosted decision trees to estimate the masses of the local group of galaxies. So at least up until a couple of years ago, and I think until now, I've not been up to date, so correct me if I'm wrong, but the total masses of the Milky Way and Andromeda were not so tightly constrained. So there's still some uncertainty about the total mass, so the total gas mass and dark matter mass that makes up the the total size of these two galaxies. And so what we did with Professor Yuda Hoffman, we used machine learning applied to our simulations to try to understand, to extract the most likely values of these two masses. And so what you can see here on the bottom side here, there's two histograms that constrain the values of the total mass of the combined system of Milky Way and Andromeda galaxies, as well as the mass ratio. So what's the ratio? Assuming that Andromeda is the most massive partner of the system, then what's the mass ratio of the two galaxies? And this is the distribution, the histogram distribution that we get using this gradient boosted decision tree algorithm. Whereas here on the right side, on this panel, you see the joint distribution of the two variables. And you see in your units of 10 to the 12 solar masses, what's the most likely outcome for the mass of this system again. And this is a nice application that brought me closer to the field of data science until I moved to the private sector. And now I'm working for in the research and development area for a company called Top Network. Is based in Italy. And we're working in the field of data science in general. And just so you know what I'm talking about, it when you mention data science, you're talking about everything and nothing at the same time. As usual, it's basically data science is a wrapper expression for everything that deals with algorithms, statistical techniques, models of machine learning, artificial intelligence, deep neural networks, everything that you can use to analyze any kind of data. So data sets can be images, can be numbers, can be text. And so depending on the data source that we're dealing with, you might be using a different branch of machine learning techniques. So might be dealing with the field of computer vision when you deal with images. The classical machine learning mostly deals with tabular data. So it's mostly numerical values where you try to find correlation between different variables that you put in a table. As well as natural language processing, that is the hot topic at the moment, as you might all know, because of all these large language models, that is like, for example, ChatGPT or Bard, that all come from these. They are all being developed within the framework of natural language processing, which is the branch of machine learning that studies how to make sense, how to analyze text in a computer, basically. So how can computers sort of process and understand text? Now, the data science workflow is very standard in a way, in the sense that usually when you deal with a data science problem, you need to prepare the data, make some pre-processing, normalization, cleaning, all sorts of operation that make the data then usable. And it's a very important phase, of course, because if you put garbage in, that you get garbage out. So you really need to make sure that your data makes sense. You don't have biases. You're not introducing any kind of problems within your data, with the data that you're actually using. What you do then, you train a model, which is a nice word to say, okay, I'm fitting some kind of complicated function with millions to billions of parameters. Usually it's in the order of thousands of parameters, which make the whole things not directly interpretable. But then you use this complicated system that has been trained on this on the data that you provide. So you get your multi-parameter algorithms to perform some kind of classification. For example, you want to identify, I don't know, there's like this very basic machine learning system that identify objects. They classify them, whether they're animals, if there's a car, if there's a human. You can do face recognition and so on and so forth. Or you can use these systems to make predictions. That's another thing that you want to do. It's predict the future. So with using this very complicated nonlinear function with functions with millions of parameters usually. So far so good. This is data science. Let's move to the geographic information system and geospatial data science side, which is what I'm mostly doing at the moment. So GIS, geographic information system, is basically everything that has to do with the surface of the Earth. So what happens on the surface of the Earth? We want to study it. It's a very general term, a sort of like a data science term. But we want to do, when we talk about GIST, then we want to look for correlations, trends. We want to gather information about some specific areas of the surface of the Earth, about transportation values. You can see here on the right, there's different layers that you can put on the surface and sort of make sense of what's happening there from different perspectives. And of course, when you're dealing with the surface of the Earth, you can look at maps, you can use drones, you can use satellites, you can just look it with your own eyes, or look at with like Google with Street View. So there's many ways that you can map the surface of the Earth and try to make sense of it, out of it. Then also with computer vision, so with machine learning algorithms. What I've been working on mostly, and what's you already know because of the name of the seminar, it's the space-borne detectors, so it's the satellites. And so remote sensing through satellites is actually remote sensing is in general whatever kind of observation you perform, mostly on airborne detectors that can be drones, for example. In this case, I'm talking about satellites. So there's, as I briefly mentioned in introduction, there's two main kinds of approaches you can have to the Earth observation through satellite-borne detectors, which is multispectral imaging, in which you have some sensor that are mostly passive, and they record basically the light that has been reflected at the Earth's surface. And they do this on many different spectral bands, which means you most likely will not just be recording the visible spectrum, so the RGB bands of the visible spectrum that make up the colors that we see then, but also some other very interesting parts of the EM spectrum, like the shortwave infrared, long-wave infrared, ultraviolet. And so all of this, of course, is very interesting and very important, because different parts of the spectrum, of the electromagnetic spectrum, interact differently with different materials. And so we can probe the Earth's surface at different wavelengths and see different processes and probe different materials. The other approach is called synthetic aperture radar. I'm mentioning here, and I will be talking about this, but just so you know, I'm not currently working actively on any project that involves this kind of detection mechanism. So I know something about it. I'm not an expert by any means, but I will talk about this because it's a very interesting technique. And so what synthetic aperture radar does is basically a radar with an active, an active sensor, in the sense that there's an active system that sends radio beams to the surface of the Earth, and these beams are reflected, and so we can study the surface of the Earth from a different perspective. And there's pros and cons on both approaches that we'll be discussing later. So I'm mentioning here just a few missions that are very famous. So from the ESA point of view, there's the Sentinel missions. There's Sentinel 1, 2, 3, 5. There's that deal with different aspects and probe the universe at the Earth with different wavelengths and different sensors as well. But let me move on and talk a little bit more about the multispectral imaging data. As I mentioned before, this, as you can see here, so on the right, you see a plot where you can see the bands that are being probed. So you can see here the basically intervals that to which where the detector is sensitive. So you can see the whole electromagnetic spectrum between 4.5 micrometers to 2.4 micrometers. And so this is the visible as well as not visible spectrum. So you have some part on the ultraviolet as well as on the lower frequencies on the larger wavelengths. So you have the near infrared and shortwave infrared. And what this system does is probing these different bands. You see you have different bands with different resolutions, as you can see in the table. So each band is being probed with a given spatial resolution, which means, for example, the blue, the green, and the red, and the number 8 here are probed with 10 meters of resolution, which means every pixel we get then will have a 10-meter size. The others vary from 20 to 60 meters. And these are sensitive also to different processes and materials on the surface of the Earth. These are the pros, of course. Then once you have an RGB image, you can see directly what's there and you can interpret it in a pretty straightforward manner. The contra is that you have to deal with the atmosphere. And so you got all the kinds of atmospheric corrections to do, humidity, winds, whatever happens in the atmosphere then affects, of course, also the light when it's being reflected, of course, towards the detector. And the most pressing problem, which is clouds. So when the surface of the Earth is cloudy, then you don't see anything. And your satellite that takes pictures on a regular time basis sometimes will take a picture of just clouds, so you don't see what's happening below that. And so there's pros and cons. But these are examples of multispectral images. This is from the area of Rome. What you see on the right, so on the left panel, you see Rome, you see the sea, there's lakes, and this is seen in the RGB. So it's just a colored image. I'm just taking the raw RGB images. Of course, the colors don't look so nice and don't look so bright. You should usually do some kind of post-processing to make the image look nicer, but it's just the raw data. And on the right, you see the near, so the near infrared spectrum photograph of the same area. Now, once you have all the information on different wavelengths, one of the first applications, which is pretty easy, pretty straightforward, but still very, very powerful, is building the so-called spectral indices. So spectral indices are algebraic combination of the bands that we gather from the Sentinel-2, for example, mission. So if you remember, we had this RGB and near infrared band from again from the Sentinel-2 mission with 10 meter with the same kind of resolution. So it's 10 meter per pixel. And we can build indices like, for example, the NDVI, so the normalized difference vegetation index, which is the one you see here. And when you subtract the near infrared to the red value and divide it by the sum of the two, then you get this index that varies between -1 and +1, and is associated with different properties of the Earth, which we'll be discussing in a minute. Same thing if you, instead of the green, instead of red, you take the green band and you subtract the near value to it, then you will get an index that is sensitive to the presence of water. Last thing is this normalized burn ratio. It's an index that is sensitive to the presence of burn there. So if there was a fire, then we can recognize it in the we can analyze, we can find it basically in the satellite images by doing this algebraic combination of shortwave infrared and near infrared bands. So let me have a few words about, okay, sorry, this is not loading. Do you see the images?
Yes, they showed up.
Okay,
yeah.
Great. So these are just what I was telling you before. If I want to make this algebraic combination of the bands, then I can get an index that varies between -1 to 1. And I can see if I just plot it on a one-dimensional color scale, so on a single color scale, then is the green areas. You see the darkest areas are associated with the presence of most vegetation with the NDVI index, whereas on the NDWI index, so the normalized difference of water index, it's you see very clearly where the water basins are located. Now, let me have a few words about the NDVI, which is a very, very powerful index because it's very strongly correlated with the presence of chlorophyll. And as you can see here on the plot on the left, you can see that the chlorophyll absorbs very strongly on the red band. So you see between 600 and 700 nanometers, there's a very strong absorption line, which means that, of course, plants do not reflect the red. And so this is why we see them as green. But you see then right before the 700 nanometers, there's a sharp drop in the absorption line, which means then when we go into the infrared, we see reflection. Basically, we don't get any absorption anymore. So this is why when you combine the two bands, so the near infrared and the red one, we can get an index that is very sensitive to the presence of chlorophyll, as you can see here. So you can see on the x-axis the normalized difference of vegetation, so the NDVI, and on the y-axis you see the concentration of chlorophyll in milligrams per cubic meter, right? And so you see they're very, very strongly correlated. It's a very good proxy. So when we study this index, we have very good feel on the vegetation that's on the surface of the Earth. And so let me have another example of this. There's a very general sort of rule of thumb that we can use. If we have an NDVI in the range between -1 to 0, then we are pretty sure we're dealing with water, snow, and clouds with a very low but still positive NDVI. It's mostly built land or barren land. There's still not chlorophyll in there, so there are not many plants. And anything above 0.2 to 1, then it's vegetations with increasing values of health or density. And what you see here below, there are maps of the harbor of Trieste that I've analyzed. I'm using these different color codes. So for you get black for the water, you get gray for the barren land, and red for the built area, so for the buildings. Whereas green, you see that different shades of green that are associated with different kind of vegetation. That, again, the darkest area being associated with the densest and mostly vegetated areas with mostly with trees. So it's gonna be you're gonna be dealing with forest or plantations, probably of tree plantations, whatever it is the case. And so this is an example. What we can do is we have access to satellites imagery databases that start from 2016 when we talk about the mission, the Sentinel-2 mission from ESA. And what you see here is this oscillations that are, of course, related to the different season. Of course, the simulation, this is the vegetation in this municipality in Sicily. And of course, you see there are seasonal patterns that are related, of course, to the fact that in the summer, the vegetation gets drier. It's pretty easy to understand. But we want to understand, we extrapolate the trend, and this is what we did. So we see that there's a trend in the last years, for example, for this municipality, that is highlighting a decline in the greenness of the vegetation in this area. This is just to show an application. Next, let's talk about synthetic aperture radar. And this is one of the most, this is a very, very important technique that works in an active way, in the sense that we have a satellite that you see here. The satellite launches a beam to the Earth, and then the satellite moves in the meanwhile. And so it gets the reflection at another point in time. And this simulates basically an antenna. It can be thought as a very long antenna. So the time that, this is the synthetic aperture that you see here. So the time that, and the travel between these 2 points is basically the length, can be thought as the length of a synthetic antenna. And so this is used to sample the surface of the Earth. Now, this thing has a lot of advantages in the sense that this, using an active device on radio wavelengths, then it is not disturbed by the presence of clouds and atmospheric corrections. And so we can get a very, very constant imagery all the time from basically from all the surface of the Earth. And so we can sample the surface of the Earth at regular intervals without, and so we can really monitor many phenomena. We can have a lot of, we can get a lot of information by looking at wavelength and polarization of the signal. So when we decide, of course, that the radar, we can choose the kind of polarization by which the wave is sent to the surface of the Earth, and then we can observe the signal back, and of course, then we can study different phenomena, of course, by looking at how the signal that is sent is disturbed, so to say, by the surface of the Earth. So what kind of interaction it has. And so again, this we don't get a full direct color image, but we can do something by looking at the polarization, for example. And so Yeah, sorry. So the pros for the SAR data, as I mentioned, is the fact that they are weather free, so they don't depend on the status of the weather on the surface of the Earth. So we can make really constant kind of images, and we can get really, we can monitor places on a constant, on a frequent basis, on a very on a fixed time basis. And then the kind of signal processing that we can apply to this signal allows us to detect variations on millimeter scales. What does this mean? I will go on this later, but it's a very, very powerful tool for some kind of phenomena. We can really analyze, thanks to interferometry, we can really see tiny variations. Now, the problem is that we don't have color information. We can sort of get some color information from the polarization status, but it's like it's more for visual rendering and get some kind of wild guess about what is going on. And again, the post-processing of these things is very complex because of all the interaction that the waves go on the surface, and all the kind of correction that we need to introduce due to the scattering of the waves on the surface. And so this is pretty complex and makes the handling of the signal quite it's quite complicated, but it can be done. Of course, there are packages to do it, but you really need to be careful. So let me show you an example of SAR images. What you see here, there are two different polarization status. So the first, so it's so VH, for example, here in the first image means simply that the signal that is sent has a vertical polarization, and then we look into the horizontal polarization channel, the power of the signal that is being recorded by the satellite. Second image is vertical. So we look again at the same image, but now we are looking at the fraction of the signal that is reflected into the vertical polarization channel. And this RGB image is a false RGB, of course. And as I said, if you mix the three, so the possible polarization channels, as I mentioned here below. So if you take, for example, the VV as a proxy for red, the VH as a proxy for the green color, and the ratio of the two as a proxy for the blue color, then we can get some kind of information about the colors. So we can see the water here, we can see the green areas, are most likely, vegetations. And for example, vegetation is taken as green because, and so VH is a proxy for green and for vegetation, because we expect the leaves to change so the signal, when it interacts with the tree, for example, it goes a lot of scatterings, and so there's a lot of power that gets into the horizontal channel because of the change in polarization of the electromagnetic wave due to this interaction inside the leaves. And so this is a reason why, just to give you sort of hand-waving explanation of why this is the case. And similar things can be said for the other colors. Now, I was mentioning very, very small variations that can be detected with SAR, so with the synthetic aperture radar. And one of these is subsidence. And so subsidence is the vertical movement. So this is whether the ground is sinking or is raising for some kind of natural or human-induced reason. So if there is groundwater extraction, usually there might be some sinking of the ground in great cities, or there might be some earthquakes or some small telluric movement that raise the the terrain. And but what you're doing with differential interferometric SAR is basically sampling, for example, a city at the same points, so on the same spatial points at different points in time, and we look at the way the waves are reflected by this point. And of course, there might be a lot of noise because there might be the reflections might change a little bit just because of vibration induced by trains, or there might be some dust or anything else that might cover or might sort of artificially raise a little bit the height of these buildings. But if we take the average of the signal, so if we look at the signal over long periods of time, over 1 year, at very regular intervals, and we can stack the signals and look at the interferometry. So if the waves gets reflected by a surface that has a certain distance from the source, and then this distance changes, then of course you get an interference pattern. So the waves do not overlap at different points in time exactly because the distance has changed. And so we can use this as a proxy as a mean of studying how the soil is changing. So how higher or lower it's going. And so these trends can be extracted. These are called subsidence trends that can be extracted by this method. And they're very powerful, and they are used pretty much. It's a very, very powerful tool, and used for this kind of application on many cities and many places. There's a very nice website on Norway that shows that subsidence all around the country, for example. So let me go to the last part of the seminar, and I'm going to talk a little bit about machine learning and artificial intelligence for GIS, so for geospatial information systems. And I don't know how familiar you are with the machine learning, but just to give you an idea, I think everyone knows what neural networks are at this point in time, though they might not be really familiar with them. But I just wanted to give a feel of the techniques that we use in the field to describe and to analyze this kind of imagery. Because, of course, when you have these terabytes of data available, you need to have an automated system that takes care of the analysis of those and looks for anomalies or looks for certain specific phenomena that we might be interested in. And so we developed within my company for a project multi-system, multi-class classification system that detects water, terrain, trees, and buildings. And it's based on this UNet architecture. And this UNet architecture that you see here is basically a deep neural network, so with many layers that go deep, and they allow us to extract some information from the images. Now, this means that every layer is basically what we are doing is taking these images and turning them into tensor. Each tensor is basically it's an RGB image is basically a matrix. There are three matrices basically. When we are talking about tensors, we are talking about n-dimensional matrices. So the x and y dimensions of the picture are the x and y dimensions of the matrix. Each pixel is just a value in the RGB or near, for example, spectrum. So we can make arbitrarily large, so to say, deep, so to say, matrices, adding more information to that if we get information from also the ultraviolet or the combination of the bands of the RGB and near bands, for example, as the NDVI or NDWI, and we feed this to the machine learning system. That in this case, what it's doing, it's UNet architecture has two parts. One is encoding, and the other one is decoding, which means we are sort of learning how to compress the image and how to decompress it, so that we learn in the process what are the most important elements. So when we compress something, we remove basically the information that is redundant and not substantial, and the system learns how to keep the important features. And so these important features is basically what allow us to say whether a piece of terrain is water or is green or there's some building in it. As I mentioned before, one of the great problems we have to deal with when we work with satellite images is clouds. So we really need to segment. So we need to identify clouds in pictures. We need to reconstruct the actual state on the ground. Of course, we need to take care that many images might be polluted with clouds, and we need to remove them. And so what we do usually, we train a system that recognizes the clouds and removes them from the pictures. And then if we take pictures at close instants in time, then we can stack these images, and we can sort of make a puzzle and reconstruct the actual status. And so we'll end up analyzing an image that has no artifacts due to the presence of the clouds. And to do cloud segmentation, of course, we also need a machine learning system like the UNet that I was discussing before. Now, this is an example of what happens when you do a terrain segmentation. On the very left side, you see an image taken from Sentinel-2. On the center, you see the mask. So this is the image that we use to train the system. So you might be familiar with the fact that machine learning systems, supervised machine learning system, need a lot of training samples, which means that they need the actual the object that we want to classify and the actual object already classified. So it learns to do that and extrapolate from the training sample and learns how to do that for other images as well. And so in this case, you see that this is the mask and this is the original image and this is the prediction. So once we train the system, we see that we get a good match of the presence of built areas, forests, and this is barren land in yellow, that we can pretty much reliably identify these structures also with these systems. Now, let me talk about the last topic that we dealt with. And again, I'm talking in this machine learning applications. I'm talking about my actual work in Top Network as a machine learning engineer. So, and it's natural hazards. Natural hazards, mostly fires and floods. And what we want to do by using satellite imagery is two kind of, there might be two tasks. The first one is monitoring. The second one is prevention. Monitoring means only that when there's a fire, for example, we want to identify in these pictures where are the most real dangerous zones, or where is the center, the epicenter, or if there are remote areas, then that might be difficult to monitor by sending people or anything. Then we might look at satellite imagery and find out where the actually we can sort of rank the risks, the actual damage that is being done, and sort of direct the and orient the rescue operations. Prevention is something that is also is more tricky, but it can be done in the sense that by monitoring some areas, so we can look at the forest and we can look, for example, the status of the vegetation. Then we know that if there are high temperatures and very dry vegetations, we can estimate that there might be a very high fire risk. And so this is the idea. So we use satellite imagery in this case to estimate the status on the ground. We can also use that for flood prevention, in the sense that satellite imagery tells us something about the moisture on the ground, and so tells us something about the capacity of the ground to absorb water. And so if there is a rainfall, then we know whether the soil is going to absorb a lot of water or not, or it's going to not to do it. So this is just to, again, to illustrate a little bit the processes that might be going on. So let me show you again. This is, for example, on actual images. How do we identify disasters? So this is in Australia wildfire in 2019. We see here the red area, and then these are where the fire started. And so we can, you see it's in a very deep forest, and so we would be otherwise unconscious about where the fire started, and simply because of the fact that it's you cannot possibly monitor all the time all the forest with persons on the ground. So, and similar things, these are floods that happened in, I think it's around the Mekong Delta, and you can identify on different, this is on Landsat and this is on Sentinel. You can see where you can use different satellites imagery so the different satellite sources to identify the extent of the flood. So you see here, this is this is sort of the RGB. That's actually some kind of corrected RGB image, and this is identified with Landsat. So you are identified on the RGB image. You are doing the same thing with Sentinel-1, and so this is the Sentinel-1 is the SAR satellite, which is the one that is it's inactive, so it's very useful for flood detection, because of course if there are floods there might be rain, and if there is rain then there's clouds, and you cannot really observe the soil with multispectral imagery. And so one project that we are implementing, and what I'm showing here is a map taken from a paper from 2022, is to build flood susceptibility maps. So once you know, this is something that you can build for knowing the properties of the soil, and then you can add to the properties of the soil that are, of course, more or less fixed in the sense that we know all the slopes and the geography and the geometry of the area. So we know also the distance from the rivers and the distance from water sources that might flood a city. We can build this kind of geographical map that is telling us the risks. And then, of course, we can add the SAR information data that gives us again, on a very constant time frequency, the information about the presence of water on the soil. And this can be used to sort of predict, but especially to monitor the presence of water in a city, for example. So it's for flood risk monitoring. Let me end then talking about fire hazard index. So this is one index that we're implementing in another project, and it's taken from another paper from 2020 that they are basically mixing different data information. So coming from meteorological data, satellite data, historical data about fires and vegetation values in a specific region. Then we can build this daily fire hazard index in this following way. And so we have this F is the fraction of live vegetation. There's this fraction of 10 hours time like soil moisture. So these are two quantities that are related to the vegetation on the ground. So the nature of the vegetation that is there, how dry is it, what a fraction of this vegetation might actually work as a fuel in the case of fires. And then there's this relative greenness index that is used that can be estimated using the values of the NDVI. So if we have a minimum value in the 5 years, so we want to really look at the historical evolution of NDVI. And so if this normalized difference vegetation index, it's on a very low level. So let me remind that very high NDVI means very good chlorophyll, and so very good vegetation status. And the other way around, of course, then if the NDVI is very, very small, then it means we want to look at, for example, exception. So if there is an outlier in the last few years, if we're extremely dry, then this, again, this value enters the formula. Now, the formula is a little bit more complicated than that. I'm not going through all the terms, but it's just to give you a feeling of how these things are built. How can we use this data to then, in practice, estimate and make some progress, so to say, about get information about the fire risks in a given area. Now, this is, to end up with, this is one of the things that we want to build, again, taken from the same paper. This is one application that was done in Sardinia. We want to look at different risks. So this was taken in June 2020 at 12. We can, using all this information and all these indices, and what we want to do is put on a map the different values. Here is the danger rate. Basically, it's just a binning of the FHI, so the danger fire hazard index. And so this is the value. It goes from 1 to 100, and then we can sort of discretize it and fit it so that we know the different dangers and sort of direct and monitor the areas that are more danger. And we can update this on a very frequent basis. And so let me conclude this talk. First of all, thank you for listening. But let me tell you that, again, cellular imagery coming from an astrophysics perspective is interesting. Also, with when it does, we have to deal with the surface of the Earth. There's a lot of abundant data. There's a lot of free data. That's also a lot of fun because there's a lot of free data sources that we can get and analyze, and everything we want to think of. So it can be sort of smoothly implemented because there's free sources with the Google Earth Engine, with Copernicus. There's a lot of missions that put their data available for free. So that's very, very, it's also motivating, and it's very good. And it's a very dynamic and innovative field of research, mainly because of the interactions with the AI community and the new satellite missions that come up every day. And I would say there's lots of practical applications that make the thing really interesting to deal with. And so, yeah, the Earth is also worth observing. Thanks a lot for listening. And yeah, that's it. Thank you.
Well, thank you Thank you very much. There should be a round of applause now.
I'll take it as a random applause. No worries.
Oh, okay. Do we? I will hide my applause. Oh, sorry. Do we have questions from the participants? Yes, Sartak,
Hey,
please.
hi.
Hi.
There is, and this was a fascinating talk, but I was thinking you say that with a like a in a time difference, you can observe up to the shift of a millimeter a year in case of
Yes.
vertical movement. So, I understand you are talking about taking two images and then their difference. But does this, is it affected, this precision, is it affected by the the orbit of that satellite? Because over time, satellites tend to decay in orbit. So will it affect the precision?
So that affects, of course, but it's something that you can correct for, because of course you can you can sort of you keep track of the orbit of the satellite, so you know exactly where it is at each time. And of course, then the other thing is that there's many other small variations, as I said, on the surface of the Earth, but again also on the orbit of the satellite, which you can sort of correct for. But the main idea is that then when you stack the signal and you get a lot of measurements, then you can extract. So you don't just compare two images; you compare them on a very large number of images on a very large period of time. So that's the thing. But you can correct for that. Yeah, it's something that you take into account. And then, of course, even if the correction is not perfect, if you get many, of course, then you get the trends, right? Because if you get many measurements, then you will reduce the noise and the statistical fluctuations, and you can extract the signal. So that's the way it works.
Okay, understood. Thanks.
Yeah, thank you.
Okay. Anyone else wants to ask a question? No. Okay. So I had a couple of questions, but one you've already answered about the publicity of the data.
Yeah. Okay.
They are free to use, right?
I mean, it depends on the resolution, but there's many missions. The ones I was talking about, Sentinel-1, the Sentinel missions are free to use, free to download. Landsat missions as well. There's a bunch of other missions that I'm talking about the ones that I know that are free. There's MODIS. There's a number of those that you can access, for example, through the Google Earth Engine. You just need to sign up and get an API. There's many other missions that are not free with higher resolution, higher spatial and time resolution. So there's the Airbus missions, Pleiades, and so on, and those are not free yet.
And my other question would be a little more astronomical. Since we have the slide with the NDVI as a good proxy for chlorophyll, the first thing that came to my mind when I saw this was to use this for extrasolar planets and look for like traces of vegetation in extrasolar planets. Do you have any comments on this?
I think it could be a good idea, but I'm not sure. So I don't know. It depends on the atmosphere of the solar planets, right? Because I guess that might be, again, clouds and stuff. So you get a mixed signal, right? So you don't get, you don't really sample the surface. You might sample other things in between. So maybe the NDVI signal might be hidden. So I wouldn't know how to correct for that on other planets. But it would be something like, of course, it would be something interesting to look at if you get sort of a clear signal from another planet and just look at at this combination of bands. And
same with water, actually, right?
The
water index.
There's also for built areas you can do something. I mean, you don't expect to find built areas in other. I mean, maybe you do, but then if you see them, then it's it's a discovery. It can be, I would say it's most likely some maybe some kind of false positive, but yeah.
Yeah, but we will have to wait for a couple of more years for sufficient telescopes to do that, I suppose.
Oh yeah.
Okay. Anybody else want to comment? Final questions? If not, I don't see anything. Okay. If not, well, thank you very much. We managed you managed to finish this time. Thank you again for a really interesting talk. Something we don't see very often, those topics here on the seminar. So I think it was useful for others to see what other people can do, what other astronomers or ex-astronomers can work on. And in this way, we end this semester of our seminars. Next seminars will start probably in March, and seems like I will be hosting them. So of course, the information will be sent in advice. So thank you everybody for participation. Thank you again, Eduardo, for presentation, and we will see you all soon. Thanks again.
Yeah.
Bye.
Thank you. Bye bye.
Okay.
Thanks again.
Okay.
Bye.